That's arithmetic growth. Let's do the same thing with geometric growth. Memory. We established that arithmetic growth is pretty good with memory. So, surprising no one, geometric growth will be less efficient. 50% of the list could be empty, right? If we double our size, whatever our proportion is, right? That proportion minus 1 could be empty. So we could have a lot of empty slots here. So that's not ideal. But let's take a look at runtime then. And we're going to assume that our array starts out with a single element, right? And that our array doubles. We're going to assume that we are doubling because it's going to make the math easier. It doesn't really matter because remember, we're talking about classifications. So the difference between 5n and 20n doesn't matter the same way that, okay, technically log base 2 and log base 5 are different classifications, but they are both log classifications. So for our purposes, we are going to consider them all the same thing. So our array is going to double every time we resize. How do we feel about logarithms? When I say k equals log 2 of n, do we all have an inherent gut understanding of what that means? I don't want to say that we do. I want to know if you do. If you don't, that's okay. Right? 2 to the k equals n. This is how you isolate k. So these two statements are equivalent. This one just has n in isolation on one side. This one has k in isolation on one side. Okay, so log is the reciprocal of exponent. Simplest way to think of it. So once again, we're doing n add operations in total. So we start off the same way. Then when we call our first resize, we're going to increase and copy one element, right? Then when we do our second resize, we need 2, right? Then we're going to need 4, then we're going to need 8, 16. How many times are we going to do this? What's going to be the last copy? How many elements are we going to copy? Well, remember, before we did k copies, right? And that's fine. We're going to do k copies here as well. But how many elements are we going to copy on that kth copy? We're going to do 2 to the k. 2 to the k equals n. We following? Can we see how we got this equation? Okay. So we're going to do the same thing we did before. Pull this guy out into isolation and simplify. Now, I believe this is called the power series. The power series. Let's call it the power series if it's not, because I'm starting to think if the power series is this. Yeah, let me not fake my calculus. This sequence, whatever it's called, this is known, right? This is why in March Madness you have a 64 seed tournament. I'm not counting the 4 playing games. You have a 64 seed tournament and you have 63 games. 2, 4, 8, 16, 32, 64. Right? That is why it works out this way. Okay? Because each branch, each game is a node between two teams. Right? So you're going to have 32 first round games, 2 to the 5, but then 2 to the 6 minus 1 total. Okay? This is why this works out that way. So we can use this equation. We can substitute it in because we can group our 1 through 2 to the k, and we can get this equation, n plus 2 to the k plus 1 minus 1. So when we have exponents that are added like this, how can we separate those apart? And if you need a concrete example, let's play with this little number here. Any ideas? Any way to derive this rule? Using 2 squared? Can you do anything with that exponent to turn it into a sum just of the exponent? See a lot of people half typing and then stopping. Come on, what can you turn this into? This value right here to make it a sum. Two to the what? There you go. 2 to the 1 plus 1. Right? This is still legal. We haven't changed anything. How do you think we can separate this out to make an equation here match these two equations here, specifically this one? Now that we got 2 to the 1 plus 1, what do you think we can do to that 2 to the 1 and 2 to the 1? Yeah, there we go. When you add exponents, you can separate and multiply. Okay? These are all equivalent statements. So using that, we can start substituting, right? And we can pull out, well, first we can put our log back in, right? Our log to the n back in. And then we can substitute out and play with our logarithms. All right, we get this. This is just 2. And x to the log base x of n is just n. Right? So because we have our exponent and our base rate, this is log is basically an undo operation. We can just pull n down. And that starts getting simple. We solve our exponent, we multiply, we add, and it means that our total runtime is big O of n. But that's our total runtime for all n adds. So if we do what we did before, we can divide it by n operations, and we can see that on average, each operation takes big O of 1. Do we all follow? We all feel okay about this? Do we have any questions? Anything we want to talk about? Anything we want to bring up? Anything that was hazy? Let's see. Okay. And we can see this if we run this code from the book, right? What this is going to do is it's going to start adding, right? So we start off with an array of 10, and then we go to 100 and 1,000, right? And we figure out the average add time for a Python dynamic array, a list, to add this many elements. And as you can see, we're pretty constant. And in fact, the bigger numbers come down a little bit, because as we resize, right, our array is getting bigger and bigger and bigger and bigger and bigger, and so our resizes get far, far, far less common. So we don't have to do our resizes as much, and we start to take advantage of the situation a little more. Now, Python doesn't do a full doubling. Python does, like, I mean, we could do the proportions above. I think it's something like 140% or something like that. It kind of tries to split the baby in half and go, okay, we're bad with memory already. Let's not go nuts here. So they're trying to find that sweet spot between the performance gain that we get by doing this, right, and the memory hit we take, right? The memory hit we would gain if we did arithmetic growth. And these files are out here. I'll pull this over. These files are out here in module 3, right? Append and size, right? Those are the ones that we just ran, as well as the book's implementation of a dynamic array. So I would strongly encourage you to take a look at those, especially the implementation of a dynamic array, because it forces Python's static array behind the scenes, and it shows you how the growth and copy and all that stuff works. So a quick review, quick summary. Now that we have all the tools at our disposal, right? We've defined this interface, right? When we defined how Python uses geometric growth for performance reasons. So if we wanted to, we could go and take a look at that dynamic array file and see how Python implements this.